So we're now going to do an example for the inverse trigonometric functions. We're going to try to compute cosine of arcsine x, okay? And we want to show that this is equal to 1 minus x squared. So let's first just review a little bit what this arcsine is. So if I take the unit circle like this, then if I here have some angle theta, and then sine becomes this height here, so let's call it y, so y is exactly this height, then these two are related by the sine function. So sine function takes the theta, the angle, and sends it to y. That's what sine does. And the arcsine is his inverse. So he takes y and sends to theta, the angle. So this is what arcsine does. So let's now just recall a little bit what we know about inverse functions. So here we can see that the sine sends theta to this height here. But of course, sine also sends this angle here. Let's call it phi. He gets the same height here. So sine of phi is equal to the same number as sine of theta. So if I were to take the inverse function of the y here, we would be in trouble because we don't know if, oops, am I supposed to get this thing here or that thing there, right? Because sine sends both of them to y. So the arcsine would be confused. Now the solution to this is to delete everything here, okay? So we restrict the domain of sine to just angles between minus pi halves and plus pi halves. Because inside of these two quadrants, the only angle getting sent to this specific y is that specific theta. So here we are restricting these guys to minus pi half and pi half. So that's restricting the domain of the sine. And then of course, the range here is from -1 to 1. So -1 to 1 becomes the domain of arcsine, and this thing here is the range of arcsine. So what do we do with this knowledge? So when we look at this thing here, I want to prove it. Well, we can use two methods. So we can use one method, which is a more geometric one, and the second is more algebraic. So let's show how to do both. So method 1, which is the more geometric one. So let me make a new drawing here. So let me make a bigger unit circle, unit potato, I would say. Then I get my y here. Or rather, I do x. So I'm putting this as x. I should also call this x here, since we have x over there. So my arcsine takes this x, gives us an angle, and then we're supposed to compute the cosine of this angle. And the cosine of this angle would be this thing here. So this is cosine theta. So now I have a right triangle here. I know, or this is my unknown. This is my x, which is kind of given to me here as the input, and I'm allowed to write my output, my answer in terms of x. And this thing here I know is a 1. Aha. But by Pythagoras, this tells me that this to the square plus this to the square is equal to that. If I solve for this, I'll get cosine theta equals to the square root of 1 minus x squared, just by Pythagoras theorem. And of course, since I'm ignoring those two quadrants, we here have a length along the positive x-axis. So there can be no doubt that there should be a plus here. This is not a minus square root. So that's the geometric method. And notice here that theta, I should write it explicitly. So theta is the arcsine of x. So what I'm writing here is the cosine of arcsine x. We could also see it here. So x is sent by the arcsine to theta. What's the second method? So the second method is more algebraic. So let's go through it. And he uses, well, it's the same thing basically written out in a different way, because we use the Pythagorean, we use the Pythagorean theorem here, and here we'll use the Pythagorean identity. So the Pythagorean identity says that cosine square plus sine square is equal to 1, which I can use now because, well, as I've said, so if I have this situation here, then theta is equal to arcsine x. So let's plug this theta in here. So this gives me that cosine arcsine x to the squared, so all of this to the squared, plus sinus arcsine x and all of this to the square. is equal to 1. But sine of arc sine x, what is that? Well, I take my x, my arc sine sends it to theta, and then sine does the opposite and sends my theta right back to the original x. So here I'm actually getting just x and everything to the square. So I'm getting x squared. So this thing here, if I move this to the other side, gives me that cosine arc sine x to the square is equal to 1 minus x squared. And then I take the square root. And let's say, so everywhere here I have equivalences, right? So here I just replace this by something. Here I just added on both sides. And now if I want equivalences here, when I'm taking square roots, I see that cosine of arc sine x is equal to, well, plus square root of 1 minus x squared, or cosine of arc sine x is equal to minus square root of 1 minus x squared. And of course, it's not necessarily so that we know which one to choose here. Now I'm trying to work as algebraic as I can. So up here, I could kind of see that, well, this cosine of theta or cosine of arc sine x, it had to be positive. And here, but here, if I just work algebraically, I'm kind of, well, let's try to reflect a bit on this. So it could be that for some x, this is the right thing to do. For other x, this is the right thing to do. But the situation is nicer than that. Why is this so? Well, notice here that my arc sine always sends theta into minus pi half by half. If I now just recall quickly how the graph of the cosine looks, well, the graph of the cosine between pi half, minus pi half and pi half, it looks like this. So it's positive there. So cosine of something between minus pi half and pi half is always positive. So it's impossible for us to have this. So we can delete this, and then we're done.